Welcome back. This is Dr. Hammond for Phys 3210, Electromagnetic Waves at the University of Windsor. We'll be wrapping up Chapter 12, discussing electromagnetic dynamics and tensor notation. We've talked a little bit about tensors, and here I'm going to review them, but we'll also be talking about tensors in terms of forces and potentials, as well as the Maxwell stress tensor. So in this lecture, I'll be reviewing some of this notation, and then I'll be discussing magnetism as a relativistic effect. So reviewing our notation, when we have this Lorentz transformation, this is using Einstein's summation notation, that this matrix lambda with superscript mu and subscript nu multiplied by x mu, this is the Lorentz transformation in position. So the 0th element is c times t, and the first element is x, second element is y, and third element is z. So of course in this matrix we would be traveling in the x direction, where gamma is this 1 over the square root of 1 minus beta squared, where beta is v over c, the speed of light. We also have this notation for when it's subscript nu, it's a covariant matrix, and when it's superscript, it's a contravariant matrix. And the only difference between covariant and contravariant matrices, or vectors I should say, is that the 0th element is just negative of the other. So this would be negative CT, whereas this is positive CT. We also discussed proper time. So this is tau, and so this is 1 over gamma, or the square root of 1 minus u squared over c squared, times t, where this is would be the ordinary time. And proper velocity eta is the derivative of the ordinary length divided by the proper time. And this is this kind of strange introduction of velocity, because you would think that the one thing that would be consistent in special relativity would be the velocity, but we introduce this proper velocity because it becomes very useful when we're discussing relativistic momentum. So this proper velocity is this ordinary length divided by the proper time, whereas ordinary velocity is just the ordinary length divided by ordinary time. The difference between proper velocity and ordinary velocity is just gamma, this Lorentz factor, 1 over the square root of 1 minus u squared over c squared. And our proper velocity in tensor notation, so this would be for x, y, z elements. For all 4 dimensions, we have that the proper velocity, this contravariant vector, is the derivative of the contravariant spatial vector divided by proper time. And so that means that these elements are c times gamma, and gamma times mu x, gamma times uy, gamma times uz. So it's easy to remember because it's just gamma times all of our ordinary velocities, and we have the speed of light is our scalar 0th order element. We also had relativistic momentum, which is just the ordinary mass, or the proper mass, times the proper velocity. And the nice thing about using this is that when we have these 4 vector scalar product with itself, then we get the contravariant vector times the covariant vector, or the covariant vector times the contravariant vector, is invariant. So it's minus m squared times c squared, where m is the proper velocity, and when we say proper mass, and when we say proper mass, we mean the mass in its rest frame. So you might have learned in first or second year courses that mass is relativistic. Here we're using this idea that the mass isn't relativistic, it's that the energy is relativistic. So here this is just the mass in its own frame. So how we create this 4 vector for momentum is that we again have the 3 dimensions of px, py, pz, where these are the relativistic momenta, but we have for the 0th element is this scalar of energy, and then we divide it by c so that the units work out. So this is kind of interesting because we've now seen that we have 3 different kinds of 4 vectors. So we have the spatial 4 vector, where the 0th element is scalar time, times the speed of light. We have the 0th order element for the 4 vector of velocity, where the 0th order element is gamma times c. And now for momentum, it's the energy divided by the speed of light. So there's a nice kind of symmetry between these 4 vectors, and we'll be seeing this later when we talk about potentials as well. Okay, so that was a little bit of a review for some of some of this notation, if you've forgotten it. But now I'm going to talk about relativistic electrodynamics and show that the magnetic field that we see is actually a relativistic effect. So what we're going to use are Lorentz transformations and the velocity addition rule to look at what happens to a charge as it goes down a wire. And this is actually a really cool effect, because you've always thought that before we started this course, or I guess before we started electromagnetic theory, you always thought that electricity and magnetism were 2 separate phenomena. And then by looking at Maxwell's equations, you recognize that they're actually linked together. But now once we do special relativity, you'll actually realize that they're the exact same thing, just in different frames of reference, which is a really cool effect that kind of like tidally brings all these ideas together. So it's too bad that this is done so late in the course, but it's really, really interesting. So I highly recommend that you follow along. So suppose we have a current carrying wire with charge density lambda. So basically these charges are packed tightly together so much that this is a continuous charge density, where we have some of the charges going to the right and some of these charges moving to the left. So this is basically what a wire does. You know, we have a current that's going to the right, and we want this thing to be neutral. And so we compensate for that by having negative charges with the same density going to the left. And sitting in the frame of this wire, these charges look like they're going to the right, these charges look like they're going to the left the same amount. So of course this electric field is going to be 0 here. And in the frame of this wire, it's neutral, and this current is going to be 2 times lambda times v. So because we have lambda times v going to the right and minus lambda v going to the left, we get 2 times lambda v as the current. So for this case, what is the magnetic field? And if we had a charge sitting here outside this wire, what would be the force on this charge? So if this were moving to the right with a speed u, how would this feel this field, and what would be the forces acting on it? So we know that the magnetic field can be calculated by Ampere's law. Of course, we have Maxwell's correction to this, but we don't have to worry about it because the electric field is constant in time. So we get that the integral of the magnetic field over this Amperian loop is going to be mu naught times the enclosed current. So the Amperian loop is going to be 2 pi r, how far away we are from this wire, times the magnetic field, and that's going to be this current of this wire times mu naught. And so the magnetic field is going to be mu naught I over 2 pi r, and this will be in the phi direction. So in the phi direction means that it's going to be going around this wire azimuthally. Okay, so now we have a charge, and so our test charge Q. In the system, we have no electric field, so our Lorentz Force Law, we have no electric field here, is just going to be V cross B. We now use U. So this Lorentz Force Law gives us Q times U cross B. U is in the Z direction, so the direction of the wire, the direction of the current. Cross B phi. And so if you remember your right-hand rule in cylindrical coordinates, this gives us QUB times negative r hat. All right. So we know that the magnetic field it's mu naught I over 2 pi r. And so this Lorentz force on this test charge is going to be negative Q U times mu naught I over 2 pi r in the r hat direction. So negative r hat means that this is attracted to the wire. So this charge is moving here, and this moves towards the wire. And that makes sense because this magnetic field is going around. And so if we were here and going up, you know, it would be going that way. No, it would be going towards it, and here it's going up towards it. So it's negative R in all directions. So it's always attracted to the wire. So that's kind of interesting, and let's remember that. Okay, so now instead of being in the frame of the wire, we're going to use special relativity, and so we're going to say what happens if we're in the frame of the charge. So now, if we're in the frame of this test charge, these charges look like they're more spaced apart, and these charges will look like they're closer together. And so that means that this wire is going to be contracted, okay? So that means that in this frame, we have to use the velocity addition rule. So we have V plus minus, where plus refers to positive charge and minus refers to negative charge. It's going to be V minus plus, U over 1 minus plus, UV over C squared. And also this charge density, we're going to have Lorentz contraction for this length, and so this charge density will also be have this Lorentz factor in it, and so times lambda naught. So lambda naught is going to be the charge density in the rest frame of the wire. And so we get this gamma plus minus factor. Okay, so now we do a bit of math where we substitute V plus minus over C, and we also have gamma plus minus, and we try and solve for all this stuff. And so you can see that this simplifies to get, so gamma plus minus gives you gamma 1 minus plus UV over C squared over the square root of 1 minus U squared over C squared. All right, good. So that's what gamma plus minus is. So now we need to know what the change in the charge density is, or the difference of the total charge density, I should say. And so that's the original charge density times gamma plus minus gamma minus. And so we can substitute this in here, and we get minus 2 lambda over C squared UV times the square root of 1 minus U squared over C squared. So this is this gamma factor. Okay, so now we're in the frame of this charge. So now we worry about the electric field instead. And so we have Gauss's law. So the integral of the electric field dot dA is going to be the enclosed charge over epsilon naught. And so we have the area is going to be 2 pi r times z, and q is going to be lambda times z, so however long we've made this box, over epsilon naught. And so our electric field is going to be this total charge density over 2 pi epsilon naught r in the r hat direction. Now, that's not the whole story. We talked about this in the previous lecture, that we're going to now look at this Lorentz Force Law. So we have the force is equal to charge times the electric field. And so now we have this electric field, we have this charge density, and we can substitute this charge density in here. And what we get is that the force is now negative Q over U R mu naught lambda V times the Lorentz factor, the square root of square root of 1 minus U squared over C squared. And we talked about how forces transform using this Minkowski force. So this force is the square root of 1 minus U squared over C squared times this F bar, this force in this frame. And so then we transform this force, and we get that this will cancel with this, of course. And so we get that this force is negative Q mu naught over 2 pi r times the current r hat. So now when we have a charge here that's sitting outside of this this wire, and it's sitting below this wire, and it's in the frame of this, if we're in the frame of this charge, then it looks like there are more negative charges here than there are positive charges. But of course we have a positive test charge here, and so it's going to be attracted to these negative charges, and so it's going to be pulled into this wire. So just like what we saw before was that we had a positive test charge moving along the wire, and the magnetic field was attractive. Now we're in the frame of the charge, and all it sees is, instead of a magnetic field, it sees an electric field, and that electric field is exactly the same magnitude as we had before, and it's attractive. And so what that means is that the force that we see in one frame is magnetic, while in the other frame it's purely an electric force. And so it's a really cool phenomenon that all we see is that magnetism is actually a purely relativistic effect, which I thought is really, really neat. And that is the end of this lecture, and I will continue with tensor notation and electrodynamics.